let me give you another example real quick here. Instead of using the book, and you may remember from earlier videos, we did some coffee filter sort of demos. Well, the coffee filter has a very, very little mass, right? So the pull of gravity isn't as great on this as it is on this. The pull of gravity. Okay. And, you know, the surface isn't as great, so the air resistance is going to be a little different than the book. But the same thing happens here. I have it at rest, I let go, and then at some point, and air resistance builds as it falls, but the gravity is still the same. And so this representation of something falling here that you see in this motion storyboard is about the same. Okay, but what does happen, and if I let me change this. Okay, let me erase this a little bit. I'm talking about coffee filter now. I'll tell you what I'm going to do. I'm actually going to just erase the whole slide and start over here. All right, coffee filter. Right. And we're going to do the exact same thing, 1 through 5 with the coffee filter. But now, force of gravity is only this big compared to the other one. Remember, before we had it down, you know, somewhere around here. Okay. But it's less mass to this object. It's not very heavy. All right, and my hand doesn't have to push up on it very hard, and so you still get F net equals 0. Well, here's the force of gravity again. Same. But now when I let go of it, there's some air resistance. Okay, there's drag. And so there's an F net that equals, okay. There's still an F net, but it's pretty small. And we see this, right? We see this filter when it leaves my hand. Okay, it changes its motion. There's a net force, and so it starts to move. But just like in with the book, as time goes on, right? We have Fg, but the air resistance builds. All right. So it builds, and now the net force is small. Smaller than, well, I'm not doing a very good job of drawing smaller, am I? Might just be easier to make this a little bit longer so we can kind of get the idea here. All right. At some point, and it's hard to perceive, and I wish I had a little bit more sophisticated equipment to do this, but right, Fg is the same. At some point, the number of air molecules in collisions creates a situation where the air resistance grows and grows and grows and is equal to gravity. And so what you get is an F net that equals 0. And you can barely perceive this, but you might be able to. We'll have to see here. Brian. Thank you. So if you watch this coffee filter, in the last maybe third, you may be able to perceive sort of a constant motion. It doesn't get faster. It may not actually, it may even occur a little earlier than that. There. Balances itself out, starts falling. And you've probably, and I'll do it again. Right there. It's moving at somewhat of a constant speed. And you've heard of this. You've heard about skydivers. You've heard about things being dropped out of planes. This is called terminal velocity. It is speed in which it is the rate in which you achieve a certain rate in free fall, and you can't fall any faster. And that is based on the idea of how heavy you are, how much gravity is pulling you, and how much air resistance is pushing up against you. And it's really a function of how big the object is. But it's because you get to a certain point where you speed up, you speed up, you speed up. Well, you're speeding up because just like the coffee filter, you have net force. So you're a skydiver, right? You jump out of a plane, and you do this with your body. Okay? You've seen movies where skydivers are, somebody jumps out of a plane and someone's chasing after them, right? So what do? In order to catch up to them, they make their body straight, right? And they point themselves down, or they fall like this. So rather than having this much surface area, they have the surface area that's equal to sort of the bottom of their feet and maybe their elbows a little bit, or whatever clothes they're wearing. And it's a smaller amount of surface area, so therefore the collisions aren't as great. And so you don't have a lot of air resistance. And the movie star typically catches up to the person who's falling like this, and then they have some sort of rumble in the sky. But I question the ability for that to really happen. But with this, it operates in the same way. You build air resistance, and if you have a big enough surface area and a small enough amount of weight, you can build that air resistance pretty quickly over time. And all of a sudden, you now have your air resistance and your gravity balancing each other, and your net force is 0, which means you're not changing your motion. Right? This is a no up here. This is a yes. This is a yes here. This is a no. There's no net force. There's nothing making you go faster or slower or change your direction. Well, if there's no net force, then you have to be, from one moment to the next, doing the exact same thing. Okay? So here's an object, or here's an example of something that can be in motion, moving, and not have a net force. And this is also a misconception a lot of people have. They think that if for forces to be present, there must be motion. Well, or if the only way you can have forces balanced is if the object is not in motion. Not the case. So you build, some people say, okay, well, can the air resistance ever get larger? Well, sure. It can get larger, or at least the push up can get larger than the gravity. And you may have heard of stories about this, but one way we could do this, right, is I could have this will be interesting to see if I can make this happen. Have it fall towards me, and I can blow on it. So now I'm adding even more collisions because I'm blowing up, right? A parachute that falls through and a large gust or updraft of wind, right, gets underneath the parachute, and what it does is it's creating more collisions, and there's more of an impact between the air and the parachute than there normally would be as it just falls through the air. And yeah, we can boost that air resistance arrow up, and therefore you get a net force that looks something like this, right? You could have a net. You could have a. Sorry, I went a little too far. You can have a net force that looks like this because this arrow grew over a period of time, and all of a sudden you get a change in motion. And if you're falling and there's a big enough net force, you can actually not only stop your fall, but push it back up. And this is what you see when I do this, right? All right. But don't get too worried about this. Well, let's sort of step back and think about what we're talking about here in these two examples. The idea of the ball kick and the coffee filter and the book all falling is just to make a simple observation that at any event, okay, you've got to consider all the forces that are acting on the object at that time. So count the interactions. Look at the objects and the number of interactions. For every interaction, there's a force. Then you can add up all of those to determine a net force. And if there's a net force, you know the object's going to change its motion. This certainly has implications for your challenge. The idea is to change the motion of the RRV in the end, right? How can we control or manage the motion of the RRV in a way that we want? Well, you have to think about the forces over time. All right, so I'm going to give you an assignment. This is your assignment 11. So I have this toy car, okay? And Ryan, can we get this front desk in here? I don't know if this is going to work or not. Okay. Yeah, this is good. We'll do it like that. Okay. So follow me over here. So we have a toy car, and you can imagine that it's bigger. You know, you can imagine a lot of things about this. And what I've done here is I've put on the screen. You can see assignment 11's got a motion storyboard. So you're going to want to use the one that's horizontal, not the vertical one. And those are the 5 chapters. It's at rest, then it's shoved forward. You can say it hit or kicked or whatever you want, but it's shoved forward. It coasts along a smooth floor. Then it rolls over a shallow carpeted doormat, you know, something you might like see in a kitchen or outside a front door. It's shallow. You know, the toy can roll up over it pretty easily. And then it comes to a rest on top of the mat. All right. So here's chapter 1, right, at rest. Chapter 2 is a shove, the moment that I make contact with it. Then it's rolling and coasting along a smooth floor. That would be 3. It is rolling on top of the mat. Okay, that's chapter 4. It's rolling on top of the mat. And then at the end, it's on top of the mat, but it's at rest. That's chapter 5. Okay? So your assignment is to draw the motion storyboard, and you're going to want to use this one. And I want you to, on your sheet, you're going to actually record all the forces and the net force, and then answer if there's a change in motion for that event.